So, basically at the burner exit, as we saw in the candle flame, the fresh air from the ambient mixes with the emerging fuel and forms a non-luminous blue color flame. Then the soot inception and growth gives the dark color, soot radiation gives the bright color, as we have already seen. So, now what happens is, when you have such a flame in the laminar regime, the flame is quite steady in nature. There will be very, very small oscillations, but the flame is quite steady. That means there is no external instabilities etc. triggered due to the flow, which is laminar in the current context. Now, when you have the fuel flow rate increased, some tip oscillations can be observed. And this is due to some external disturbances or the instabilities which are created due to the entraining oxygen from the ambient. So, tip oscillations can be observed at certain fuel flow rate. One more thing is, in these 4 cases, we have seen that the flame tip is closed. Here it is closed and we do not see any visible smoke. Why? Because what is smoke? We already seen the definition. Smoke is nothing but some carbonaceous soot particles coming along with the products of combustion, gaseous products of combustion like CO, CO2, H2O, N2 etc. Now, in these cases, we have shown that this color is due to soot inception. That means soot is formed and it radiates also as a bright color. So, soot formation is there, it also radiates to impart a bright color, but the soot is oxidized well within the flame height. So, soot in these 4 cases, soot is oxidized well within the flame height. So, no visible smoke is seen. That is, the soot particles coming out along with the hot products of combustion will actually impart a smoke layer coming out of this. Actually, what happens is, if you increase the flow rate say beyond this value, then the tip can open and the smoke can come out. But that is not visible here in these cases because of the fact that the soot which is produced is oxidized well within the height of the flame itself, so that the visible smoke is absent. So, again, this is one of the characteristics of the diffusion flame, that you may not have complete combustion when you drive more and more fuel and only allow the oxygen to come from the ambient through diffusion. If you do that, what happens is, you may not have a complete combustion, or soot also can form and escape, because the soot may not be able to oxidate itself within the flame zone, so that it will leave. So, there will be some residence time required for all these phenomena to happen. So, if there is no residence time for the soot which is formed to be oxidized, then the smoke will appear. So, that is a weak point of the diffusion flame. The strong point of the diffusion flame is, see, when I told about the premixed flame, we told that when you want to establish a flame in a burner port, basically there is a small range of flow rate which we can assume or which we can operate on for a given equivalence ratio. Then only the flame will be established, or else the flame can be lifted off or it may flash back. There will be 2 instabilities which can happen. But this operating range is much wider in the case of diffusion flame. Okay. So, the main point here is, the operation range of the diffusion flame can be wider, but when you do it in this way, increase the flow rates etc., you can have a flame which is formed, but there will be some smoke formation or incomplete combustion, or the flame will lift off from the base etc. So, these are also possible. So, now let us see what is smoke point, which is very important for us. So, as I told you, in the range of the flow rates considered in this slide, okay, 2.7 to 5.6 LPM for LPG, we have shown that the smoke does not appear over the flame, that is the soot particles formed or oxidized within the flame. But if you see this series of photographs, the first two cases A and B, again I form a flame which is closed, having a closed tip, and when you go to the third flow rate C, you will see that the tip opens, the closed tip opens and the smoke comes out. So, the minimum flow rate at which you can see a visible smoke, okay, the flow rate or say minimum flow rate of the gaseous fuel at which visible smoke is found at the flame tip, like this, visible smoke is found, that flow rate of the gaseous fuel is called smoke point. Okay. So, at low flow rate what happens? The soot incepted will be oxidized within the flame height itself. So, no soot particles exit the flame and only the hot gas go out. So, we do not even see that unless you just go and touch at a particular height of the flame tip. But when you have higher and higher flow rates, there will be no residence time for the soot to oxidize. Okay, soot oxidation depends on the residence time, availability of oxygen and OH radical also. So, if you have higher and higher flow rates, one of the components can be deficient, so that the soot may not be fully oxidized within the flame itself, that leaves the flame tip and along with the hot gases, and a visible smoke is seen. That minimum flow rate at which you can see that is called smoke point. Okay, that means there is the lower than that flow rate you will not see any visible smoke, only at that flow rate and higher than that you can see visible smoke above the flame tip. So, that is very important characteristic of a diffusion flame, and this is basically dependent on the flow rate at which this smoke is seen is dependent on the fuel type itself, whether the fuel can form soot, at what rate it can form soot, and how the soot can be oxidized, etc. These characteristics will dictate the smoke point, that is the minimum flow rate at which the flame tip opens and visible smoke layer comes out, that is the soot plus hot gases. See, for liquid fuels and gases, the solid fuels, the diameter of the or the area of the burning area, what I can say, the area of the solid fuel or the liquid fuel, when you increase it, basically what happens is at a particular area you will see the smoke formation. Okay. So, that means basically if you try to have a larger area, then it burns at a the mass burning rate will be higher, that will contribute to soot formation, as well as the soot may not be oxidized within the flame height, so that it leaves as a smoke. In several big fires, you will see lot of smoke because of the fact that the soot which is formed cannot be oxidized within the flame itself and comes out as smoke, which is actually very dangerous for us. So, now let us see some values of smoke point for some fuels. Say for example, take propane. Propane and N-heptane. Propane is C3H8 and N-heptane is C7H16. So, now if you see this, the mass flow rate of these fuels at which a visible smoke is seen, the minimum mass flow rate is given as about 7.9 milligram per second for propane and 5.1 milligram per second for N-heptane. These are the values of smoke point. Propane is a gaseous fuel, N-heptane is a liquid fuel. So, now go to unsaturated fuels, propylene, acetylene, etc. Okay. So, saturated fuel is CnH2n plus 2, unsaturated will be CnH2n, etc. or 2n minus 2 and so on. So, now you see that at a much lower flow rate itself, I get the smoke point. Instead of say propane, you can just compare 7.87 milligram per second, the smoke point reduces drastically to about 7 times to 1.12 because of the fact that these unsaturated hydrocarbons can produce more soot. When there is an unsaturated hydrocarbon, basically the precursors for soot are compounds like C2H2, C2H4, etc. And now these compounds can be present at higher, like for example, in acetylene, propylene, etc. These compounds are also present, or when they disintegrate, these compounds are present, that will form more and more soot. So the soot production rate and its oxygen rate will have a mismatch, so that the smoke formation occurs at a earlier or a lower flow rate when compared to the saturated hydrocarbons. So unsaturated hydrocarbons, basically several materials of fire are unsaturated, have the mixture of saturated and unsaturated, more proportion of unsaturated hydrocarbons. So the smoke formation is inevitable. Similarly, when you go to cyclic structure, benzene, toluene, etc., still the smoke point is much smaller. Okay. So for example, if you say C6H6, then you see that the number of carbon atoms is comparable to that of hydrogen. That means the ratio of carbon to hydrogen, if it is higher or if it is increasing, then the smoke point will reduce. So that we can say. So smoke point is the minimum flow rate at which visible smoke is seen from the flame tip, and this smoke point depends on the nature of the fuel, whether it is saturated hydrocarbon or unsaturated hydrocarbon, and so on. So now let us see some features of diffusion flame. As I told you, the visible length or the extent of the flame is one of the important characteristic of a diffusion flame. So going back here, we can see that as these are all laminar regimes only. We can see that flames are well behaved. They are, even though smoke point is reached, you can see the flames are well behaved, not much oscillations, and the surface is smooth. So these are the characteristics of laminar diffusion flames. And as the fuel flow rate increases, the flame length increases. So what is the flame extent? Typically, we see that there is no much radius change in the radius of the flame, but the height of the flame increases. So we can say that the visible length of the flame is one of the important characteristics for the jet flames or candle flame, etc. Now we will do a simple scaling analysis to understand the factors which influence the flame length. Okay. Please understand one more thing here, that the transport of fuel to the flame zone, transport of the oxygen to the flame zone dictates the flame extent or flame location, flame zone location or the flame boundary. So the chemical kinetics is basically very fast. When the fuel and oxidizer mixes the stoichiometric proportion, immediately they are consumed. That mixture is consumed. Okay. So that means that the chemical kinetics can be assumed to be infinitely fast. Okay, that means that the flame can be assumed as a thin sheet of zero thickness. For theoretical analysis, please understand that as I told you in the structure here, where typically you get the maximum value of the temperature, a sharp point, and a sharp point where the concentration of fuel and oxidation goes to zero. These are the same location. This is the flame center point, or you can say that the flame can be assumed as a thin sheet theoretically. but obviously there will be some leak across the flame zone, so that the flame has a finite thickness as seen in the structure. So now here, for the scaling analysis, let us say that the chemical kinetics is infinitely fast. That is, whenever there is a mixture of stoichiometric proportion formed with fuel and oxidizer, immediately it is consumed in the flame. So the chemical reaction rate is much faster. That means the flame thickness is can be approximated as a thin sheet of zero thickness. So that is one of the main thing. Second is, when you take a flame coming from a port, the flame can be drawn like this. Okay, so now you see that the flame, basically the fuel particle coming out of this, say a fuel particle, goes to the flame radius, or fuel particle from this goes to the flame tip also. The transport of the fuel particle from the burner exit to the flame tip occurs by convection, because there is a momentum for the fuel jet which is coming out. So in the axial direction, the fuel particle is transported due to convection, but in the radial direction, which is perpendicular to the axial direction, only molecular diffusion supports the transport of the fuel, correct, because there is no convection in this direction. So by molecular diffusion, what is molecular diffusion? Due to concentration gradient. The fuel particle is transported from the center to the radius, flame radius or the flame surface, where it meets the required oxygen. So for a jet diffusion flame, molecular diffusion is predominant in the radial direction and convection occurs along the axial direction. So that we have to understand. But please see that if the flame is steady, then the time the particle at the burner exit takes to reach the fuel tip, flame tip, the particle at the burner exit, the time it takes to reach the flame tip will be same as the particle at the center of the axis to reach the flame radius or the surface. Okay, now in the laminar regime, the molecular diffusion, we have to estimate some molecular diffusion time. So for that, we define a molecular diffusivity. For example, how fast a fuel diffuses towards the oxidizer. Molecular diffusivity, which has a unit of meter square per second. So this may be DFO, the diffusion coefficient between the fuel and the oxidizer. Okay, now if the fuel molecules travel a distance y in the radial direction, it may be r also, then as per Einstein's diffusion equation, y square will be equal to approximately 2 times diffusion coefficient or diffusivity into time. So that is the Einstein diffusion equation. Now what I do is, I change y as r, because let us say, even though, see, if you see the flame at some axial distances, the distance traveled in the radial direction is different for each axial location. But let us take an average value and say it is r, the radius of the burner itself. So let us say that in the radial direction, on an average, a fuel molecule travel through a distance of the radius of the burner r. So y is replaced by r, so that I can say by Einstein diffusion equation, r square will be proportional to 2 dt, or the time it takes for the fuel molecule to diffuse from the center of the burner to the flame radius is r square by 2d. So that is the time scale for the diffusion in the radial direction. Now convection, the fuel molecule is in the burner port and it travels this height of LF, which is called flame length or flame height. Okay, now let us say that average velocity with which the fuel comes out is the burner exit velocity VE. So, the average velocity is VE. So, what is the time taken for the fuel molecule to convectively get transported from the from the burner exit to the flame tip? So, the time taken for the fuel molecule to convectively transport itself from the burner exit to the flame tip will be T equal to LF by VE. Now, please see that this flame has to be intact or steady. That means the time taken for the convective transport should be same as the time taken for the diffusive transport in the radial direction. Convective transport in the axial direction, the time taken for that should match the time taken for the radial transport. So, I can say R square by 2D should be equal to LF by VE. Okay. So, now from this I can get an expression for the flame length LF equal to VE R square by 2D. Okay. So, VE is the average velocity of the jet, fuel jet which is coming out at the burner exit velocity. R square is the radius square. So, now what is the volumetric flow rate of the fuel? QF. Volumetric flow rate is the area of cross section of the burner port into the average velocity, exit velocity. So, area of cross section meter square and this is meter per second. So, volumetric flow rate will be meter cube per second. So, now replace this VER square by QF by pi. So, I get LF goes as scaling analysis QF by 2 pi d, that is it. So, that means in the laminar, so far we are investigating the laminar regime where the molecular diffusion is predominant. So, in the laminar regime, what we have seen is the flame length is dependent on the volumetric flow rate of the fuel. And inversely proportional to the diffusion coefficient. When the diffusion coefficient is smaller, then the flame height will be larger. If volumetric flow rate increases, the flame extent will be higher. So, one more thing what you have to understand here is the volumetric flow rate basically depends on both the burner radius and the velocity. See, for example, if a volumetric flow rate is the same, I have a larger burner, then the velocity will reduce. I have a smaller burner, then velocity will increase. Okay. So, basically what we can say is the laminar flame, diffusion flame, the height of that depends on the volumetric flow rate and inversely proportional to the diffusivity of the fuel and the oxidizer. So, this is very important. So, this is got by a scaling analysis and which is what is demonstrated here as the volumetric flow rate liter per hour can be converted to meter cube per second. As the volumetric flow rate increases, you can see the visible flame height increases correspondingly. Now, let us see some diffusion flame regimes. That is, when you take a gaseous fuel coming out of a port, a fuel coming out of the port, a flame is formed. So, it has a velocity, say VE, the burner exit velocity, and it has a particular length. LF is the length. Okay. Now, due to, see, when I say a flame is formed over the burner, the flame is hotter, the flame surface is hotter where the reactions are taking place, the ambient is colder. So, there will be a natural convection which is set up. That is why you see the flame actually elongating. If you do the same experiment in zero gravity, the flame height will not be so much or microgravity. In the normal gravity, the flame has a certain height LF. This is actually caused by the convective transport as well as the buoyancy. The buoyancy force is nothing but the natural convection which is driving this basically, because of the fact that the flame surface is hotter and the ambient is colder, and the hot particles rises up and the cold ambient air comes in, and this actually elongates the flame. There is a induced flow around the flame. So, let us take the Froude number, which is nothing but the ratio of initial jet momentum to the buoyancy force. Okay. So, the initial jet momentum, what is initial jet momentum? When the gas jet comes out of the burner pipe, what is its momentum? The momentum actually, in open case, basically we can say just take an isothermal jet. When the jet comes out and goes into open environment, its momentum is actually conserved, but the velocity decays. So, these are the characteristics. Now, let us say take the initial jet momentum, which is calculated based upon the jet exit velocity VE, and the buoyancy force. Buoyancy force, see, let us take the flame surface which is having some height. This is like a hard plate of a particular length kept vertically oriented, and you see that induced flow comes from the ambient. So, the flame height, basically throughout the flame height there will be induced flow due to buoyancy. So, that is the characteristic scale for the buoyancy force is the flame length. So, for the momentum it is jet exit velocity, for the buoyancy it is flame length. So, now what causes the buoyancy? The gravity. So, that means that the acceleration due to the acceleration of the flow due to the buoyancy is dependent on the normal gravity 9.81. Now, literature shows that this acceleration exactly not same as 9.81, but it can be approximated as 0.6 times g into the temperature gradient drives the buoyancy force. So, that is also taken into account. So, what is the temperature gradient here, temperature difference here? The flame temperature, ambient temperature, and normalized with respect to the ambient temperature itself. So, this expression is the acceleration or the order of the magnitude of acceleration which the flow encounters. Okay. So, now the Froude number can be written as VE square divided by A into LF, the acceleration into LF. So, the VE square represents the momentum, initial jet momentum, and A into LF represents the velocity scale which is induced by the buoyancy. Okay. So, root of that will be velocity scale basically. So, the regimes of diffusion flames can be categorized based upon the value of the Froude number. If the Froude number is of order of 1, then the initial jet momentum as well as the buoyancy force dictates the flame length or the flame characteristics. When Froude number is much greater than 1, that means the initial jet momentum controls this. The buoyancy effect is lesser. So, the initial jet momentum, or we can say the flame is momentum controlled. Okay. The third case will be when the Froude number is much less than 1, then it is completely buoyancy controlled, because the buoyancy driven acceleration dictates the flame characteristics. In most of the cases, we will end up in the Froude number approximately equal to 1 case, where both the jet momentum as well as the buoyancy force will dominate or dictate the flame characteristics. So, these are very important. So, the flame height, what you get here in the normal gravity is dictated by the jet momentum as well as the buoyancy, and the flame Froude number will categorize that as momentum controlled or buoyancy controlled or controlled by both. Now, let us see some important flame height correlations, which are basically developed by or reported by Roper based upon experimental results. So, these are all empirical correlations. So, there are correlations available for circular ports or rectangular ports, square ports, etc. But we will not talk about all this. You can refer the literature for that. The correlation for circular ports goes like this. Based upon several fuels, several tests, Roper has formulated this. So, he says that the flame length is equal to 1330 into the flow rate of the fuel meter cube per second, and he also considers the difference between the ambient temperature and the fuel temperature. For example, fuel temperature, the jet temperature can be higher or lower than the ambient temperature itself. So, that ratio also he considers, divided by natural logarithm of 1 plus 1 by S, where S basically is an important parameter, which is the molar stoichiometric oxidizer to fuel ratio. You know what is air to fuel ratio, defined during stoichiometric studies, that is the mass of the air divided by the mass of the fuel. But when you do it in molar basis, S is the molar stoichiometric oxidizer to fuel ratio, you will see that it is nothing but the number of moles of S equal to number of moles of oxidizer divided by number of moles of fuel. That is it. So, and QF the volumetric flow rate. So, this is a very simple correlation. Again, from a scaling analysis, we saw that LF depends on QF. The same factor is coming on here. Now, what is S? In simple terms, S for a hydrocarbon of CXHY can be written as X plus Y by 4 by, this is mole fraction of O2. Generally, it is 0.21. So, that is the S value. So, I will stop here and continue in the next class.